monoxyl acid, you're putting a monoxyl acetate to make malate. That malate leaves. When you get that malate out, in the cytosol, we can produce NADH. We're going to oxidize that malate to OAA, giving us an NADH. That NADH, the NADH to NAD ratio goes up, and that's going to help drive this reaction in the forward direction. So there we are with glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate plus DHAP. We got fructose 1,6-bisphosphate. No energy, fructose 1,6-bisphosphate to fructose 6. That came off as an inorganic phosphate. No energy. Fructose 6 to glucose 6. Reversible reactions. Glucose 6 to free glucose. No substrate level phosphorylate. So our energy costs are right here. What? Dehydrogenase. Yeah, it does. Well, we have one. That's minus 1 NADH. And that's cytosolic. And guess what? We got one right here. So that cancels out. Those cancel out. So it costs us 1 ATP, mitochondrial NADH, what? 2.7 ATPs. Hello. Rewind the tape. So, somewhere back there on a disk that you have in storage from last quarter, it should tell you it's about 2.7, right? So that's minus 2.7. So I've got minus 1 plus a minus 2.7. It's already costing 3.7 ATPs. Pepsi K, 4.7 ATPs. Glycerate kinase, 5 ATPs. Well, they're not really confused you. What's the cost? We took pyruvate, 1 mole of pyruvate, and we made half a mole of glucose. It cost us 1 ATP plus another 2.7, so that's minus 3.7 ATPs, 4.7 ATPs, 5.7 ATPs. Plus, you might throw in another 0.27 here or there. So I got minus what? 1, 3.7, 4.7, 5.7 ATPs. It cost me 5.7 ATPs to make half a mole of glucose out of a mole of pyruvate. And if I'm trying to make a mole of glucose, i.e., enough glucose that I can make 180 grams of glycogen, if I'm trying to make that, it's going to cost me twice that. It's going to be about minus 11.4 ATPs to make a mole of glucose out of pyruvate, out of alum. And that doesn't count. That doesn't count the fact that I'm going to have to spend some energy later in the quarter to get rid of that damn nitrogen that came off the alanine. So I'm at 11.7. What is this? About 32.5 ATPs. I spent 1/3 of my energy making that glucose. I'm the athletic advisor for animal science. Why would you run around a track when if you ate a high-protein diet, you're losing energy? Eating that steak is exercise. I'm telling you. And this is why that diet works. That's one of the reasons. Because it is amazingly expensive to make glucose. Yeah. So right directly behind you, we have glucose and phosphate. Yeah. And we go phosphoglucose under it. Yeah, there's glucose 6. Oh, location. Location. Got it. Okay? Yeah. What's this?
What's the enzyme?
Aldolase A. Yes. As opposed to aldolase B, and that's going to become important when we talk about fructose metabolism. Pretty simple pathway. It's just basically the reverse of what we did last quarter. Okay. I got one important point. Control. Is there what? No. start conjugating glucose 6-phosphate into the end-plastic thickening result. All right. Yes. Yep. Yep. Absolutely. So that GTP, it's really, in my opinion, it'd be worth more than one ATP because this is cytosolic GTP. So I had to get it out of the mitochondria, just like I do an ATP. I had to get this sucker out of the mitochondria, and that's going to cost a protocol. So that's 0.27 of an ATP. So you can actually add on 0.27 of an ATP, and you can get this thing damn near 12. So 2.7 times 0.3 times 2 is 6. Yeah, I can get 12. I can make it cost me 12 ATPs if I want to charge myself for that protocol. Absolutely. What? Easier to look at this now here, but that's how they cut the structures. Yep.
Again, from your product on the far left, where it says phosphate, you said that's alkylate A, right?
Yeah.
It's supposed to be like...
Alkylate converts fructose 1,6 bisphosphate to glycerol like bisphosphate with blissful reaction. Okay. So let's look at this and think about it. Gluconeogenic amino acids, that's what we just did. Now, what's not on this diagram is that's going to dump off an amine group, and we're going to have to do something with that amine group. What we're going to do with that amine group is probably lose it as urea. So we're going to have to deal with the urea cycle. And we'll do that at the end of the quarter. And there's a cost for putting that nitrogen onto urea. So there's going to be more cost. It's expensive to get rid of nitrogen. So I'm not only exercising by converting my alanine to glucose, I've also got to deal with the nitrogen. Well, lactate. I don't like this diagram because it doesn't show the difference between the gluconeogenic amino acid and lactate. Lactate, pyruvate, is a lactate dehydrogenase. So if I'm taking lactate to pyruvate, I'm going to take NAD and make NADH. I couldn't do that with pyruvate. If I'm increasing my NADH to NAD ratio in the cytosol because I'm dealing with lactate, I don't have to do all this rigmarole with the malate to the oxaloacetate. Don't need to do this. I'm already raising my NADH ratio. That NADH is going to be used right here. Oops. I have it set to the right side. That NADH is used right here to make NAD to drive that reaction forward.
Big black line.
So the difference between how you deal with the pyruvate depends on the source of the pyruvate. If the pyruvate came from lactate, lactate to pyruvate results in an increase in NADH to NAD. Put that in your delta G equation and figure out what that means for 1,3-bisphosphoglycerate and glyceraldehyde 3-phosphate. If we're increasing that NADH, we're increasing the substrate, we're going to go the reverse direction that we did last quarter. So one of the controllers for this reaction is what's the NADH to NAD ratio. It's more of a mass action thing. Delta G is really just a equilibrium function. So lactate, we can come out either as aspartic acid, or we can come out as PEP because we have the ability with Pepsi K to take this oxaloacetate and make PEP. And that's going to cost me GTP to a GDP. That PEP can go right through here, and we don't have to do all the Hufen and Hoffen right there. There appears to be a differential in gluconeogenic animals and humans as to the expression of that PEP-CK enzyme, whether it gets more expressed in the cytosol or in the mitochondria. So there's some interest in looking at that. Whether this oxaloacetate goes out as PEP or as aspartic acid depends on a whole different issue. If you're going to send oxaloacetate out as aspartic acid, you have to have glutamic acid to make aspartic acid. So if we're sitting in here with OAA in the mitochondria and I want to send it out as aspartic acid, I have to have glutamic acid for my transamination. That gives me alpha-ketoglutarate. So I've got the same problem that we looked at with malate aspartate shuttle. The only reason this would work is if I have an abundance of glutamic acid and alpha-ketoglutarate that I can shuttle back and forth through the mitochondria and cytosol. And that may not be the case. Nonetheless, we've got three ways to do this to get PEP right here. One is by converting the OAA to malate. One is by converting the OAA in the mitochondria to PEP. And the third one is to convert the OAA to aspartic acid in the mitochondria, send it out into the cytosol, and then you turn it back to glutarate, make glutamic acid, and convert the aspartic acid back to OAA. Okay? Gluconeogenesis in a nutshell. What? Move it up a little bit. All right. A couple of side notes. That PEP carboxykinase, PEP-CK, the delta G for that physiological condition is about a minus 22.5 kilojoules per mole. So it's highly safe. Where PEP-CK is depends on the species. And just briefly, the rat has it in the cytosol. The rabbit has it in the mitochondria. The human has it in both. So we end up using the rabbit and the rat a lot in especially nutrition studies, and they're both a pretty poor example of a human. You're way better off with the guinea pig. The guinea pig has it in both places. Has PEP-CK in both places. The fructose 1,6-bisphosphatase. The delta G under standard conditions is somewhere in the neighborhood of a minus 16.7, and under physiological conditions about a minus 8. Some control notes you should make. Pyruvate carboxylase. We have two regulatory enzymes in the body that don't function. They are turned off without an activator. One of them is pyruvate carboxylase. You have to have acetyl-CoA present for pyruvate carboxylase to be active. As you increase acetyl-CoA concentration in the mitochondria, you're going to increase the activity of the PEP-CK. In the absence of acetyl-CoA, pyruvate carboxylase. In the absence of acetyl-CoA, that reaction won't take place. Here's part of the basis to that. To lead us into where we're going to be going. If you look at the mitochondria in the matrix, we've been bringing pyruvate in. It can go two places. It can go to acetyl-CoA. You can go to OAA. This pyruvate carboxylase will not function without acetyl-CoA being present. Hey, you've got pyruvate, you're making acetyl-CoA. If you're making acetyl-CoA out of pyruvate, it's being chewed up pretty quickly. It's going into that PCA cycle. You're going to drop off your CO2s and come back to OAA. So we're going to pick up our citrate. And with acetyl-CoA make OAA. We'll keep things going. When acetyl-CoA levels go up, that's going to activate this thing. Acetyl-CoA levels are going to go up when you're low on energy. Out here in the adipose cell, our regulatory mechanisms we'll discuss ad nauseum. We're going to be converting the triacylglycerol that you stored in that adipose cell into non-esterified fatty acids and glycerol. Those non-esterified fatty acids in the blood are going to show up in the liver cytosol. In the cytosol, we're going to take that non-esterified fatty acid, and by hook or crook, I'll show you later, we're going to put that non-esterified fatty acid as a fatty acetyl-CoA. It's going to end up in here, so we're going to have a fatty acetyl-CoA, and we're going to degrade that thing to acetyl-CoA, and make some NADH and FADH through the process. When you're short on energy, this is activated. When you're short on energy, you're going to increase NEPAs in the blood. When you're short on energy, those NEPAs are going to end up as fatty acetyl-CoAs in the mitochondria. They're going to be used to produce acetyl-CoA, so you can run acetyl-CoA through the PCA cycle. Just in making the acetyl-CoA, you're going to get approximately one NADH and one FADH2 for each acetyl-CoA. You'll peel off that fatty acid. We're going to have a big increase in acetyl-CoA. If your acetyl-CoA level's going up, the system says, I've got plenty of energy. My problem is making sure I've got plenty of glucose for all those tissues that have an absolute glucose requirement. So acetyl-CoA goes up, it's going to have a positive effect, and that's why. Acetyl-CoA is going to go up in that mitochondria, either when you're low on energy and you have this system running, and that's going to be the primary one, or sometimes when you get the epinephrine shock, because that'll also increase the need, we'll show you that. So that's one control. And the basis for that acetyl-CoA control is that acetyl-CoA goes up in the mitochondria when you're in an energy-poor state. So it doesn't make sense, does it? I thought we took acetyl-CoA and we could run it through the PCA cycle and make energy. Well, that's what you're doing, but the acetyl-CoA that's going up here is coming from fatty acids. And those fatty acids are being released because your glucagon levels are up. Glucagon goes up, you're going to start dumping fatty acids out of the adipose cell. That's one component. Second component. Well, pyruvate dehydrogenase, we don't have to worry about it. Acetyl-CoA levels are up. We're going to inhibit pyruvate dehydrogenase and inhibit making acetyl-CoA anyhow. So this fatty acid going to a lot of acetyl-CoA, that's going to inhibit pyruvate dehydrogenase. So that gives us carbon skeleton going this direction. So we don't have to. That's going to help prevent kind of a futile cycle. So we're good to go from PET on up to fructose 1,6-bisphosphate. Then we have a regulatory side, fructose 1,6-bisphosphate. Because of the presence of the flip side enzyme, TFK, we go that direction and throw it in ATP. So there have to be some controls there. We talked about some of them. AMP is going to be a big control. So AMP is an effector. I think I got it better. I got a neat slide. is out of Harkness. Follow the thing through. You never know when you're right in front of the line. We got fructose 1,6-bisphosphate that came from pyruvate. We're headed for fructose 6-phosphate. We're going to use fructose 1,6-bisphosphatase to do that. There's a number of allosteric controllers. One is that fructose 2,6-bisphosphate we talked about last quarter. We said fructose 2,6-bisphosphate is an allosteric activator of PFK1. It's an allosteric inhibitor of fructose 1,6-bisphosphate. Fructose 2,6-bisphosphate is produced from a protein that does two things. This is your protein. It does two things. In the phosphorylated form, the protein is inactive PFK2, and it is active 2,6-bisphosphatase. In other words, if I have this little protein phosphorylated, it's going to convert fructose 2,6-bisphosphate to fructose 6-phosphate. There's not much fructose 2,6-bisphosphate around. It's a messenger. That's all it is. It's a messenger. So it's not going to have much impact on flux. If this protein is dephosphorylated, it's going to be active PFK2, and it's going to make fructose 2,6-bisphosphate, but it's going to inhibit 1,6-phosphate. What controls phosphorylation and dephosphorylation on there are two things: protein phosphatases and cyclic AMP-dependent protein kinase. So guess what? Low on blood glucose, cyclic AMP goes up. Cyclic AMP, because of glucagon, cyclic AMP is going to activate degradation of triacylglycerols. We're going to end up with fatty acyl-CoAs over here. They're going to make a lot of acyl-CoAs. That's going to slow down pyruvate dehydrogenase, activate pyruvate carboxylase. At the same time, that cyclic AMP is going to activate a pKa. That pKa is going to phosphorylate this protein. And when you phosphorylate this protein, you have active 2,6-bisphosphate, or active 2,6-bisphosphatase, and it's going to convert that fructose 2,6 to fructose 6, and we're going to lose that inhibition. So we lose the inhibition in the presence of glucagon. And in the presence of glucagon, with that inhibition released, we're going to convert our fructose 1,6 to fructose 6. With insulin's going to have a couple effects. Insulin is going to decrease cyclic AMP because it activates the phosphodiesterase 3 that we talked about last quarter. So insulin has a negative effect on that cyclic AMP. Insulin is negative. Has a negative effect on cyclic AMP. And it has a positive effect on that protein phosphatase 2. So insulin up against a high carbohydrate diet, you are going to have active PFK2, so you can get all that glucose, all that carbohydrate rate down to pyruvate. So the pyruvate goes to the mitochondria, and the mitochondria makes acetyl-CoA, so it's a TCA cycle running. ATP goes up, ATH goes up.